Hey class, so this idea of testing our geometry against the view volume, it's actually a little bit expensive. So I'm going to write this out here. Testing every vertex of every triangle. Let's see if I can write neater than that. Against the view volume is very expensive. Still cheaper than rasterizing if we don't need to, right? Which is quite expensive. And there are faster ways. Okay, but we'll come back to some of those faster ways. But there's a property of geometry that's really important, and that is many shapes end up being clustered together. And I'll explain what I mean by that. So many shapes are clustered together. So if we have these clusters of objects, maybe we can test. Can we test as a group? Of course I did. Can we test as a group? Right? So this is what the next topic is about. We use what we'll call bounding volumes. And the idea is really simple. The idea is we realize that our geometry is often clustered. We wrap the geometry in some kind of volume that encapsulates all of it. We test the wrapping, we test the bounding volume against the frustum, and then if it fails, then everything inside fails. So it's like a hierarchy. We have these bounding volumes. It saves us a lot of work. So the first approach I want to talk about is a bounding box. So a bounding box is really simple. We calculate a volume that surrounds our geometry. Calculate a box. Surrounding a collection of geometry. Okay, and then we test the box against the view volume. So let me draw out what this might look like. Imagine you had this model. You had a person, right? And they have hair, and they're wearing a hat, and they have arms and a body. Maybe they're wearing armor. Maybe they have a sword. You know, this is a really complicated model. So I'm going to say this is a complex shape. I'm just making up a number here, but imagine that we have 10,000 vertices, which isn't that crazy for a really complicated shape. So imagine we have 10,000 vertices. So with what we said above with view volume testing, we need to take each one of these vertices and test it against our view volume. Okay, but instead we do the following. One, we pre-calculate a bounding box around the object. Okay, and we can do this ahead of time. It doesn't need to be online. I'm going to just draw it here, right? We could imagine a box like this, and it's really easy to come up with this box. You just min and max your coordinates, right? You go through all the vertices, find the minimum in each direction, and you have it. I should probably draw this a little better. Anyway, I'll just do it again. Okay, and then the back one comes down. There we go. So we have this box. We put the model in the box. And then once we do that, all I have to do is I test the 8 vertices of the box instead of 10,000. So you see now the the complexity we went through just up here of having these 6 planes and coming up with point tests and calculating where these planes are and then checking if points are on either side of the plane seemed like a lot of work if I'm doing a triangle. But suddenly, wait a second, if I can exclude or include 10,000 vertices, wow, that's really, really efficient, because with a simple test that we can do with just 8 vertices, we can include or exclude the whole collection, right? Exclude or include the whole shape. There's an alternate method. Okay, there's an alternate method. Instead of a box, we can actually use a bounding sphere. Okay, we can use a bounding sphere. So if we have some kind of complex geometry, we can actually just draw a unit sphere around it. Not unit, but a fixed size, a uniform sphere, not an oval. We can actually draw a sphere around it. We can define that around the geometry. Right, and which is simply a center plus a radius. So this is really simple, similar. I mean, these are really similar approaches. They're slightly different in that, you know, the box can do elongated shapes and whatnot. Spheres, the way that we typically do it, they're actually circular, so you have some limitation there. But the sphere turns out to be a simpler test. All you need to do is ask your engine if the distance from the center to the plane, right? If that distance between the center of your sphere and the plane is bigger than your radius, then you call it, right? And let me draw that out for you. So you imagine I have a plane here and I have a sphere. Now all I do is I take the distance from the center of the sphere to the plane, and then I compare this distance with the radius. In this case, the distance is bigger than the radius, the sphere is outside. In this case, it just equals, so you can consider it outside. In this case, the distance is less than the radius, so you can see that it's inside. In order to make this work, we do need to think about how to calculate the distance from a point to a plane. But I'm going to toss that into the next video so we can keep the math isolated. But I do want to quickly say one more thing, is that you can have bounding box hierarchies. So you can actually nest these things, which is really cool. If you have a really complex object, like a head, arm, body, and you have this really complex thing with a lot of geometry, the sword, right? And you expect some things to be on screen, some things to not be on the screen. You can actually construct bounding boxes, right, around each different geometry, like that. And then you can have it, the other arm has its own box, and then the whole body can have one box. So if, right, you can imagine that if it passes and the model is visible, imagine a mountain or something really large or really complicated, then you can then do another check on all the sub boxes. Okay, well, how about the arm? How about this arm? How about the torso? The head? As long as all of the pieces are covered in the sub boxes, you can nest and nest and nest and nest. So you can actually nest bounding box hierarchies to be more flexible. I should say bounding volumes, actually. So you can nest bounding volumes into hierarchies. So you have more flexibility, because if you have a really complicated model and it becomes all or nothing. That can be very expensive, even if you only expect a part of it to be visible. Okay. All right. So we'll stop here, and we'll come back, and um, we'll learn about the sphere test.